Hi everyone, in this video I am going to explain depth first search in design analysis of algorithms. So depth first search. So here I discussed about this topic in design analysis of algorithms under decrease and counter method. Right, so this is an algorithm. So first of all we try to understand this algorithm, so then we can solve this particular problem. Okay. So now this is an algorithm for DFS. So now we have to take one graph. So this is a forest actually. So see, you can observe that there is two graphs. So now there is no connection between this graph and this graph, right? So such type of graphs is said to be a forest actually. So now we can apply this DFS algorithm on this graph a little bit later. So before that you are going to understand this DFS algorithm first. So then we can solve this problem. So now in depth first search, we can apply on this graph. So these are the comments. So that implements a depth first search traversal of a given graph. So input is a graph which consisting the vertices and edges. So capital B. So capital B is nothing but set of all your vertices. Capital E is all of your edges, right? So these are all vertices like A, B, C, D, E, F, and G. H, I, J. So these all are the vertices which comes under this capital B. So whereas capital E, all the edges. So here you can observe that this is an unweighted graph. So there is no weights on edges. So because of that it is said to be unweighted graph. So now what will be your output? So now your graph G with its vertices marked with consecutive integers. So in order they have been first encountered by the DFS graph. So now this order will gives you like in which order you are going to travel your DFS of this particular graph. So that is given by an integer values here. Okay. So now you can start the algorithm. So see here. So this is means you can mark each vertex in B with 0 as a mark of being unvisited. So now you can take the set of capital B, so which consisting all the vertices like A, B, C, D, E, F, G, H, I, and J. So all these vertices is a set of B. So now you mark all the vertices of B with 0. So now initially all are zeros. So A 0, B 0 and C, because all the vertices are unvisited at this state. So now you can initialize your count with 0. So now you can start the count, because we are every time we are incrementing this count value and we are assigned to this vertices, which gives an order of we are inserting an elements into your stack, an order which you are popping from the stack. Right. So before that we have to remember DFS algorithm is used to implement by using stack. So stack is nothing but it's a data structure. So where the insertions and the deletions can be taken at the single place. So which is said to be a top of the stack. So this is also said to be a LIFO, because the last inserted element is to be deleted first, right? So it will follow the LIFO fashion. So now you can initially you can initialize your count variable with 0. So what we can do now, so for each vertex B in capital B, so these are all the vertices. So these can be represented with small b, right? So now for a capital B, do. If B is marked with 0, so see, if any of the B is marked with 0 is nothing but the vertex is not visited as of now, right? So then you can apply DFS of B. So for that vertex you can apply the DFS algorithm, right? So now what is your DFS of vertices will say? So see, visit recursively all the unvisited vertices if connected to the vertex B by a path, and number them in the order they are encountered. So via a global variable counter. So here once you visit that particular vertex, you have to increment the counter value. So and that count value you can assign to that particular vertex B. So for each vertex W in B adjacent to B. So what is the meaning of that? So for every vertex, some other vertices are connected. So those vertices are said to be an adjacent vertex to the current vertex which you are going to see. So now you can take that adjacent vertices and you can see if W is marked with 0. So what do you mean by if any vertex is marked with 0? That indicates that that vertex is not visited. So now you can apply for that adjacent vertex to again DFS. So what your DFS will say? So you can take the vertex again and you are trying to find the adjacent vertex to that, and you can identify that if any one of the vertex is not visited yet, then you are trying to visit that vertex and you make the count is to be incremented and you can assign that incremented value to that particular vertex. So this is an algorithm. So now I'll show you. So how you can solve this particular graph, means how you can apply this DFS algorithm for this graph. Right. So I'll start with the vertex A. Right. See here. So now what this A, B and C will indicate is, see in this example DFS travel, A is a graph. So this is nothing but your graph. Right. And then you can see here B is nothing but traversal stack. So now this is the content of your stack. So here you can observe that there will be two values. So here the first value which indicates that the order in which the vertex was visited. Means suppose if this vertex C you have the value as 3, that is nothing but at third time you can visit this D. Right? Means you are first visited A, then C, then D, like that. And the second value means see here, it will gives you the popping position from the stack, right? See, second one indicates the order in which it became a dead end. So that is popped off the stack. So and whereas this C, it is a forest, DFS forest. So with the tree edges shown with a solid lines and back edges will shown in a dashed lines. Right? So I'll explain you about this a little bit later. We just go through that. So now we can start with the vertex A. So I'll start with the vertex A. So now I'll mark it. So initially this vertex is marked with 0 because this is unvisited end. So now, so I can increment my count value by 1 because I just visited this vertex A. So now the count value is 1. Right? See here, you can observe that the count value is 1, right? So now I'm trying to find what are the unvisited vertices with this particular vertex. So now I'm finding of that I have 3 vertices from A. So one is C, another one is D, another one is E. Right? So now these are the 3 vertices adjacent to my vertex A. Right? So now I'm trying to take this adjacent vertex, again I can apply DFS. So what your DFS will say, again I need to find what are the unvisited vertex from C. So now see, you just increment this value. So here it has become, so initially the count value is 2, right? So now it becomes 2. Because I need to increment the count value for this. So now it is 2. And so from this C, I'm trying to see for this, these two are unvisited because from A I'm trying to visit this particular node first. So the count value is 2. So now from this C, I'm trying to visit all the remaining unvisited vertices which is connected to C, that is D and F. So now from C, I have D and then F. So now I can increment D by 1. So now the value is 3 here because after C I am going to visit my another vertex D. So now that count is 3. And from that D I am going to visit the unvisited vertices. See, this is your D, right? So now these are 2 adjacent vertices A and C. Now you are finding of that A and C is already visited. A and C is already visited. See, because A value is not 0 and C value is also not 0. So then this is said to be dead end. So this is said to be dead end because I didn't have any other possibility to move from D. So this is my first dead end, right? You just remember. So now I can give this dead end positions after this I'm visiting all the vertices. So now see, so the next one is F. So now I'm coming here. So I can increment my counter value. So now this will becomes to 4. So after this F, I'm going to see the another unvisited vertices. So I'm finding two vertices. So one is B and another one is E. So from these two unvisited vertices, I'm trying to see my first vertex as B. So I just increment my count value. So now it becomes 5. Right, now it becomes 5. So now I can see that from that 5, so from that B, I have one more vertices which is adjacent to that. So that is E. So now E is unvisited, so that from B I am trying to take this E value. Right, so from that I am trying to take this value E. So now you can remove these two because you are not taken this value from A. So from C you are taken B. So like that, so that I just remove this edges. So now B is assigned with 5 and E is assigned with 6. So now you can observe these suffixes. See, I first visited A, and then I visited C, and then I visited D, and then I visited F, and then I visited B, and then E. So see, 1, 2, 3, 4, 5 and 6. So which vertex is going to be become a first dead end? This one. So now I just remove D first. And after that I can find out that this is a dead end because from this I didn't take any of vertices to reach. So now this will be a second dead end. And now and after that I can see this is my third dead end. Right? And after that, so your F is becomes to the fourth dead end. And then your C will be fifth dead end. And A will be the sixth dead end. So because of that, it will given you the suffixes values like this. See, A, 1, 6. Now you're finding 1 and 6. So this is the order which you are going to push into stack. And this is the order which you are going to pop from the stack. So now you are popping D first, and then E, and then B, and then F, and then C, and then A. So now tell me the order. So now you can take D first, and then E, and then B, and then F, and C, and A. So for this internal graph, you are getting the order like this, right? And then now I'm showing the external graph. So from this external graph, so I'm started from vertex G. You can apply the same thing, right? So now you can start from Z. So from that Z, because initially G, H, I, J all are having zeros only because all the vertices are unvisited. So now, so I can start from Z. So I can find out that here two unvisited but adjacent vertices. So now that is H and J. So I can take this one first. So see here, you just remember your counter value is 6 here. As on completion of your internal graph, your counter is 6. So now your G is becomes the counter value is 7. So which is inserted the order into your stack. So and then this value is 8 because after G I am going to visit H. Right? And after that, from that H, I am going to see the another adjacent vertex, that is I. So now this is I, right? So the count of this is 9. So now it becomes dead end actually. See here the order is given G is 7 first, and then H is 9, and then I is, sorry, H is 8 and I is 9, right? So and then this is you just backtrack and you're getting, see, this will be dead first. So now you can take this is 7 because here the dead end is 6, right? So now this is 7, and after that this dead end is 8, and this is not a dead end. See, because see here this will be, we can travel from G. So from G you can view the another unvisited vertex G, J. So now this value counter it gets 10, and now this will be the dead end. So this value of dead end is 9 and this is 10. So now you are getting, so this will be your first dead end. So because, so which node is said to be dead end? From that node you are not visiting any other nodes. Means from that node you are finding all the adjacent vertices are already visited. So such type of vertex is said to be a dead end. Okay. So now here, so this is an order we are popping. Means tell me in which order you are going to pop now. So now after A, so this is I and then H and then J and then G. So now this is your DFS order according to this algorithm, right? According to this algorithm, so this will be your DFS order, right? So I cannot say like every time you are getting the same order, because from A here I am traveling C. So because of this I am getting this order. Suppose from A if you are going to travel D, then you are getting the another order. Or else from A you are trying to visit E first, then you are getting the another order. So for BFS or DFS, you just remember, so one order is not your solution. So you can have any order, depends on that in which order you are going to visit all the vertices which is connected to your current vertex. Okay, so this is a depth first search using your decrease and conquer method. I hope you all can understand. Thank you.